Good evening, Year 11, and welcome to the night before your physics exam. So, on paper 1, the following topics are covered: the particle model, atomic structure and radiation, energy and electricity. Atomic structure also comes up in chemistry, so if you've had questions about the structure of atoms or the alpha particle scattering experiment on your chemistry exam, you will not get them again on your physics exam. If they haven't appeared on the chemistry exam, they may well be on the physics paper. Firstly, don't forget you have the equation sheet with all of the equations that you are going to need written on it. I'd like to point out at this point that it is also double-sided. Please check both sides of the equation sheet. If a question asks you to refer to it, then please make sure you thoroughly check to make sure that you find the correct equation. It will tell you exactly which equation it's looking for. It will tell you the quantities that are in it. All you have to do is match up the formula on the sheet with the information given in the question. There are some questions that are higher tier only. They are highlighted on the formula sheet, so if you're doing foundation tier, you needn't worry about those ones. If you're doing triple, you get the same equation sheet as shown here as well. There are 4 required practicals as part of the Year 10 content which can be assessed on paper 1. The resistance of a wire practical and the density practical have not come up in the last 2 or 3 years on the exams, so I'm going to spend a little bit of time talking those ones through with you. The current voltage characteristics has, and the specific heat capacity has as well. That came up last year. However, it's still worth revising those in case questions about them come up. So, the resistance of a wire practical requires you to have an ammeter, a voltmeter, a power supply, which could be a battery, a meter-long ruler, and the piece of wire that you are testing. You will need wires with crocodile clips so that you can connect your circuit to the wire that's being tested. Importantly, when setting this circuit up, you have to make sure the ammeter is connected in series and the voltmeter is connected in parallel to the wire. It's also important that you use a relatively low voltage, no more than 3 or 4 volts. The wire is exposed, it doesn't have any insulation, and so will get hot, and therefore there is a risk of you burning yourself if you touch it. If the question asks about including a safety hazard when you're describing the method for this experiment, that is the main one that you need to mention. So, for this experiment, you would be changing the length of the wire. That would be your independent variable. You would be measuring the voltage and the current, and then using that to calculate the resistance using Ohm's law. So the resistance is the voltage divided by the current. So the way this experiment works, you set up the circuit as shown in the diagram, and you can either start with the longest piece of wire or with the short piece of wire. That doesn't make any difference. As you can see here, it's set up at the 100 centimeter end. So we have one wire connected to the 0, one wire is connected to the 100 centimeter end. You switch it on, you measure the voltage and the current, and you switch it off. Don't leave it on for longer than necessary, as the wire tends to overheat. Once you've got your results recorded, unclip it from the 100 centimeter position and move it to the 90. Switch it on and record the voltage and current again, and then repeat the process, going down in 10 centimeter increments until you've only got to 10 centimeters left. That will give you a range of values that are evenly distributed for you to calculate the resistance of the piece of wire. You will then be asked possibly to put them into a results table. The length of wire, being the independent variable, will go in the column on the left. The resistance, being the dependent variable, will go in the column on the right-hand side. From there, you could be asked to plot a graph of your results. When plotting a graph of the results of the resistance of a wire experiment, the length being the independent variable goes on the horizontal axis, the resistance being the dependent variable goes on the vertical axis. You should find that you get a straight line graph that goes through the origin. If you have any anomalous results that don't appear to match up with your straight line, please don't draw your line through them. It should always look like the one you can see here. The word we use to describe the relationship between these two variables is directly proportional. Anytime you have a straight line graph that goes through the origin, that is the phrase that you need to use to describe the relationship. The other thing that could come up in relation to this, you could be asked to compare the results from two different types of wire or two thicknesses of wire. If you have a thick wire, its resistance will always be lower for any length. So you would get a line that has a gradient that is shallow, like the one you can see here in red. If you had a very thin wire, its resistance would always be higher for any length. So you would get a line that is steeper, as you can see here shown in green. So if you're asked to compare different wires, the thicker the wire is, the lower its resistance for any length. So you'd have a shallower gradient like this. The second required practical is the density required practical. Now, this could include a regular shaped object such as a cuboid or a block. It could include an irregular shaped object, and previous years have mentioned chess pieces, little tiny statues or random pieces of rock. Or it could be to calculate the density of a liquid. Now, in order to do any of those things, you do need to know the mass of the object and its volume. And describing how to measure those things will be part of the method. So for all of these things, the piece of equipment that you need to use to measure the mass is a set of scales, otherwise known as a top-pan balance. For any solid object, you just place the object directly onto them and it will give you a reading for the mass. If you're dealing with a liquid, then you need to place an empty container on the scales and zero the scales and then pour your liquid into the container, and that will give you the mass of the liquid. Or you measure the mass of the liquid in the container and then you subtract the mass of the empty container. Either method is perfectly acceptable. To calculate the volume of a regular shaped object, you need to measure using a ruler the length, the width and the height of that object, and then multiply those three things together. For a regular cuboid shaped object, the easiest way to do that, to ensure that you always get the right three side lengths, is to pick a corner and measure the lengths of the three sides that come off of that corner. That way you won't accidentally measure height twice, width twice or length twice. For a liquid, to measure its volume, you need to pour it into a measuring cylinder or similar accurate piece of measuring equipment, and the volume that you get on the scale there, which will be in millilitres, would be equal to its volume in centimetres cubed. 1 milliliter is equal to 1 centimetre cubed. And once you've got that information for either of those shaped objects, you can calculate density by doing mass divided by volume. For the irregular shaped object, you have to do the volume in a slightly different way, and there are two possibilities. For larger objects, you would use the displacement can, otherwise known as the Eureka beaker, as you can see in the diagram at the top. With this piece of apparatus, you fill the beaker up until the water starts to drip out of the spout. That way you know it's completely full. Make sure you then empty any containers you've got under there. You then place your object into the displacement can. It will displace a volume of water equal to its own volume. That water can be collected in a measuring cylinder, and then the volume of that water is equal to the volume of the object. For smaller objects, such as a small rock, you can use water directly into a measuring cylinder. Place a known volume of water into the measuring cylinder, record it, add your object. As it sinks to the bottom, the volume of the water shown on the side of the scale will rise, and the difference between the volume there and the volume before is equal to the volume of the object. And again, you then use the density equation, mass divided by volume, to calculate the density of your object. Okay, coming away from the required practicals, there are a few key words that you do need to know the definition of, the meaning of, and you could be asked to state these as part of the exam. So the specific latent heat is the energy required to change the state of 1 kilogram of a substance without raising its temperature. When a substance is changing state, its temperature always remains constant. The energy is going into changing the state of the substance and not raising its temperature. Now, every substance will have two values for its specific latent heat. There will be a specific latent heat of fusion, which is for the change of state between solid and liquid, and the specific latent heat of vaporization, which is for the change of state between liquid and gas. That change of state requires more energy, and so the value for the specific latent heat of vaporization will always be higher than the specific latent heat of fusion. The second definition that you need to be aware of is the one for specific heat capacity. This is the amount of energy required to raise the temperature of a kilogram of a substance by 1 degree centigrade. It is important that you mention both the mass and the temperature rise in the answer for that question if you're asked to describe what it means. Both of these quantities have a formula associated with them for doing calculations with, which is found on your formula sheet. They only appear in one equation, so if you're asked to use it, there is only one equation with those things on. Both specific latent heat and specific heat capacity can also be referenced in the form of a graph, as shown on the screen here now. So when a substance is in the solid state and is being heated, its temperature will go up. The gradient of that line can be used to calculate the specific heat capacity. The steeper the line is, the lower the specific heat capacity of the graph. Less energy is needed to raise its temperature. As the specific heat capacity changes between different states, the angle of that line can change, as you can see here. When it is changing state, the line remains horizontal because no energy is going into raising the temperature stays constant, all of the energy is going into changing the state. So on the diagram here you can see where the substance is melting and also where the substance is evaporating. The line for evaporating is longer because more energy is required to change the state from liquid to gas than is required to change the state from solid to liquid. If you look at the value that is associated with that horizontal line, that will tell you the melting temperature and the boiling temperature of that substance. Moving on to electricity and how to wire a plug. As you can see from the diagram here, the inside of a plug contains 3 wires and a fuse. The 3 wires have very specific names: the earth wire, the neutral wire and the live wire. They also have very specific coloured insulation around them. The insulation around the live wire is always brown. Around the neutral wire it's blue, and around the earth wire it is green and yellow stripes. The live wire is also connected to a fuse. The purpose of the fuse is to melt in the event that the current becomes too high, for example, in the event of a power surge. The fuse is designed to fail and therefore protect the component at the other end of the plug cable from overheating and getting damage. Fuses are very easy and cheap to replace. A brand new television could cost you a lot of money. The live wire is where the electricity comes into the device. The neutral wire is where it leaves to go back to the main supply. There is a potential difference of 230 volts between those two wires. The earth wire is there as a safety feature. Normally there is no electricity running through the earth wire, but in the event of a fault, then electricity will return through the earth wire and back to the fuse box and down into the ground underneath your house to be safely dissipated into the surroundings. If the earth wire was not present or not connected, there's a possibility you could get electrocuted. The earth wire, though, is only found in electrical devices that have metal casings exposed, so ovens, washing machines, things of that nature. Any electrical devices that have no exposed metal casings don't need an earth wire because there is no possibility of you touching them and electrocuting yourself. So in devices that have completely encased in plastic, then they quite often have no earth wire. Also, from the electricity topic, you need to be aware of the difference between the types of electricity you get from batteries and the type of electricity you get from the main supply. From batteries, you get something called direct current. This type of electricity has a fixed value for potential difference. It is always positive, and it provides a single current which is also in the positive direction. The main supply of electricity is called alternating current. In this type of electricity, the potential difference is constantly changing between a maximum positive value and a maximum negative value. When it does that, the current changes direction, going positive and negative. This type of electricity is found in our main supply at home, and there are two numbers that you need to know associated with this. They are 230 volts at a frequency of 50 hertz. That means the mains electricity supply alternates between a potential difference of plus 230 and minus 230 volts, and it goes through a complete cycle, one complete wave, 50 times a second, hence the frequency is 50 hertz. That means during that cycle, very briefly, the potential difference and the current are both zero as the electricity changes direction. Moving on to the radiation topic, there are two key phrases here that you need to be able to define and understand. The first one is the half-life. The half-life is the time it takes for half of the radioactive nuclei in a sample to decay. That is a fixed amount of time. It is unique to each individual radioactive element and each of its isotopes. It could be fractions of a second, it could be minutes, hours, days, weeks, months, years, thousands of years, hundreds of thousands of years, or even millions of years. It's just a time. The longer that time is, the more stable the element is. So the most unstable radioactive elements have half-lives of fractions of a second, whereas those elements that are almost stable can have half-lives of millions of years. The other quantity you need to be aware of and be able to define is the activity of a radioactive sample. That is a measure of how many nuclei are decaying every second. and that is measured in units called becquerels. Following on from half-life, you could also be asked to plot or be presented with a question that shows you a half-life graph. The half-life graph will always have this shape. It always starts with a very large value at time 0 and falls very rapidly and then gradually levels out to approach 0, but it never quite gets there. On exam questions, they may not give you the entire graph, they may give you just the left-hand side of it. The horizontal axis will always be time, but again, check the units because it could be minutes, it could be hours, it could be days. The vertical axis could be any one of these quantities. It could be activity, it could be the number of nuclei, it could be the amount of a sample or the mass of a sample, it may even be percentage. Doesn't make any difference in terms of the half-life calculation because the answer will always come out to be the same. So the information you need in order to calculate the half-life from this graph, the first thing you need to know is what is the value at time equals 0. And if you look at this graph here, you can see the line at time equals 0 is at 200. What you need to do then is to go to half of that value, and once you find that value, draw a line across to the curve, and from the curve go straight down to the time axis. The point at which that line crosses the time axis is the half-life for that substance. Now, when you do this on a graph, on an exam paper, you're going to use a pencil, you're going to use a ruler. There is always a little bit of leeway in the marking of these exams. There is an answer they are expecting, but they will allow you one small square either way of the answer they're expecting to allow for the fact that some people's pencils might be slightly thicker than others and some people might not be drawing a perfect straight line. Usually on the graph paper on the questions, the lines on the graph paper do line up exactly with where they want you to get the value. So that's always worth looking for.